first with 4 questions sent to me by Professor Rajendra. So these 4 questions, 3 of them were raised while I was present during the session, and one was introduced later to the list. So first question I shall read out. So initially we will begin with these questions today. So the first question that was given to me, and I could not answer that at that time right away, is Maxwell's boundary conditions lead to the generation of 2 refracted rays at the surface of a birefringent medium. So here, incidentally, Professor Rajendra has been sent. I mean, please just look. I mean, this question found in the book of optics by Jenkins and White, right? Just the name is Fundamentals of author Francis Jenkins and Harvey White, White, Jenkins and White, McGraw-Hill edition, Fundamentals of Optics. So those who are in the answer to this question may please note the section in the chapter of double refraction, section 26.9, chapter 26, section 9. So theory of double refraction. So I'll just briefly refer to the basic principle of this, the answer to this question. Of course, there will be a good deal of details to work out, and in fact, the details are not even present in the book of Jenkins and White. The authors have referred to another book by Peter Drude, Theory of Optics, where the full details have been worked out. I haven't looked into that book, but anyway. So let us now try to understand what is happening over here. How Maxwell's boundary conditions, well, let's not talk about boundary conditions, just the Maxwell equations itself. Maxwell's equations themselves will give the idea about why we get 2 refracted rays, right, even without any reference to the boundary condition. So let us see. The answer is connected to anisotropy. If you recall our discussion yesterday, we discussed with regard to calcite, which is here. I mean, I discussed the properties of calcite. Here, it is an optically anisotropic crystal, right? So calcite, quartz, these things, extraordinary rays are produced in optically anisotropic material. So here, let me just touch upon the answer that I'm reading out from the section of the book 26.9, chapter 26, section 9. Only in the case of an isotropic substance like glass is it permissible to write, the electric displacement vector is written as D is equal to epsilon into E. Now, in anisotropic crystals, it is found that the measured values of the dielectric constant epsilon, this is the key point, the dielectric constant epsilon varies with orientation of the optic axis or axis relative to the electric field. Now, if you remember that we are talking about optics over here, and optical properties of a material are captured, or at least some very important optical properties of a material are captured by the refractive index n, and the refractive index n is equal to square root of the dielectric constant. Well, actually, square root of the product of epsilon r and mu r, but mu r is usually, which is relative permeability, that is usually equal to 1. So for all practical purposes, we take n, the refractive index, to be equal to square root of the dielectric constant. Now, in an anisotropic material, yesterday we discussed a few things. For instance, for the E rays, the refractive index has a different value as compared to O rays. So it immediately means that different direction, so different refractive index values will correspond to different dielectric constant values. And the fact that, so once again, I'm reading from this book, the fact that the dielectric constant, or epsilon, varies with direction in these crystals. Uh, so this variation of the dielectric constant with respect to direction in crystals is the key factor over here. This variation of epsilon with direction in these crystals can be shown by electromagnetic theory to give rise to double refraction. So the to the question that how Maxwell's boundary conditions, I wouldn't even say Maxwell's boundary conditions. I would say even it's more basic than that. How Maxwell's equations, I would say, how Maxwell's equations lead to the generation of two refracted rays at the surface of a birefringent medium. So basically, what will happen is that as soon as you have a different value of the dielectric constant, then immediately you will have a different velocity, because velocity of light depends on the permittivity and the permeability of that material. So immediately you'll have two different values. And so here in Jenkins and White, it is said that it is found for any direction of the wave front, there are two velocities for the vibrations of the vector d. Vector d is the displacement vector. So the displacement vector d is equal to, usually we write displacement d is equal to epsilon into the electric field E, right? So in this case, when it is usually when it is an isotropic material, the epsilon value is the same in all directions, but in an anisotropic material, the epsilon value will change from one direction to another. So that's the basic idea. Of course, there are more details to be worked out. So the generation of refracted rays is this. The last thing that I shall just read out is that this line: it is found that for any direction of the wavefront, there are two velocities for vibrations of the vector d, which is the displacement vector, in two mutually perpendicular directions, and this is the fundamental aspect of double refraction. So basically, um, it's anisotropy. Anisotropy results in different values of the dielectric constant in different directions, and accordingly, the Maxwell equations will have to be adjusted for various components, and accordingly, you will get different rays, two rays. I mean, two different velocities, and so you will have an ordinary ray and an extraordinary ray. So that was hopefully, and if anyone is interested to um, refer to a proper electromagnetic theory text, although I will refer to David Griffiths. So this question has not been explicitly or in any wise addressed in David Griffiths, but there is in chapter 9 a good deal of discussion on obtaining the basic laws of geometrical optics. That is, the incident ray, the reflected ray, and the refracted ray, they all lie on the plane of incidence. That's the first thing. Then the angle of incidence is equal to the angle of reflection. That's the second thing. And then Snell's law, which is the third thing. So how you could derive them from electromagnetic theory, Maxwell's equations, that thing, this feature has been discussed in David Griffiths' book on electromagnetic theory, Introduction to Electrodynamics, in chapter 9, section 9.3.3. So you may refer to this thing. But in an electromagnetic theory book, Griffiths' book is a standard book. I haven't found any reference to this, how you can get two rays from Maxwell's equations in an anisotropic material. So, I'm just giving you a passing reference. I just gave you the basic hint, but of course, I have not been able to work out the Maxwell boundary conditions. But in Jenkins Griffith's book, there is the reference to P. Drude's book, Theory of Optics, where apparently the full mathematical treatment has been provided. Anyway, so that was the first question. I hope I have been able to give some satisfaction to the person who asked this question. Question number 2: why do ordinary rays obey Snell's law strictly while extraordinary rays do not in birefringent crystals. I mean, I have not found any answer in any of the optics books or anywhere else so far. I will try. We still have one more day to meet, but I mean, I have, I shall try to make an educated guess as to this answer. You see, ordinary rays um obey Snell's law, and Snell's law is set with respect to a basic geometrical framework. What is the geometrical framework? That there is an incident ray, there is a refracted ray, there is, I mean, it's all geometrical optics, and there is a reflected ray. And then there is the interface between two media, the where the reflection and the transmission or the refraction happens. So there is the interface, and perpendicular to the interface there is a normal. So Snell's law is a geometrical law because you talk about things like sine of angle and all of those things. So Snell's law is effectively a geometrical law with reference to this basic geometric framework: ray paths, normal, the refracting edge, refracting interface, all of these things. My educated guess is that I mean, Snell's law will hold in all isotropic material, right? Whereas anisotropic materials do not have to fit into this proper geometric framework. They could go off all these geometric lines. And since extraordinary rays appear only in anisotropic materials, so probably the basic framework of basic geometrical framework of Snell's law, that framework does not apply to extraordinary rays because of anisotropicity. Because anisotropicity means that it'll go by a different kind of geometry, right? Like yesterday, we discussed the propagation of O rays and E rays. O rays follow a neat spherical or well, on 2D a circular front, whereas O rays become elliptical, or in three space or in three dimensions they become ellipsoidal. So anisotropic conditions may need not adhere to the simple geometry of isotropic materials, and Snell's law is based on the simple geometry of isotropic materials. So probably that is the reason. But once again, I have to say that I have just given a phenomenological provided a phenomenological description. Of course, there will be a good deal of physics depending on the nature of materials and the behavior of electromagnetic waves in materials, and how the electromagnetic waves bring about polarization in the atoms and molecules of that material, and that's how extraordinary rays will form. In fact, with reference to the previous question, how Maxwell's equations can lead to the generation of refracted rays, there is a good deal of discussion on how polarization is brought about in anisotropic material by an electromagnetic wave propagating through it. So, in case you can download Jenkins White's book from the internet or procure it, please look at section 26.9 for the answer to this question, the question number one. Question number two, I'm just giving an educated guess as to why extraordinary rays need not obey Snell's law. Because once again, I'll say Snell's law follow the simple geometric framework that happen in isotropic materials, and ordinary rays follow that geometric the framework of geometrical optics in that. Okay. Question number three: how birefringence arises in optical fibers, and what acts as a filter for light oscillations in optical fiber cases? Now, this question has got two parts. So, as to the second part, I haven't been able to get any answer. Probably it is beyond my expertise also. What acts as a filter for light oscillations in optical fiber cases? I'll try to see if I can find an answer to that. But for the first part, how birefringence arises in optical fibers. You see, birefringence is the outcome of anisotropic behavior, optical anisotropic, which means that if you have an optical fiber material which has anisotropic optically anisotropic properties, then you will have birefringence. Now, whether it is a part of the design or not, I cannot say. Sometimes what happens is that imperfections in the fiber material can bring about the anisotropic behavior, or stress, because long ago I myself worked on some simple laboratory experiments as a university student on optical fibers. I did realize that an optical fiber gradually becomes loses I mean becomes denatured, so to speak. The light becomes faded over time with exposure to the atmosphere. The material degrades. Those I have seen. So probably external stress, heat stress. Because of heat or mechanical stress, bending or whatever. All of those things can bring about imperfections in the optical fiber material, and that could give rise to anisotropic behavior. And if there is anisotropy, then the possibility of birefringence is very much open. So that is probably, the first part is probably answered by that. I don't know how birefringence arises in optical fibers. Okay, let us now go to question number 4. Uh, in polarization optics, if the ordinary and extraordinary rays form an entangled pair, how does the difference in their propagation velocities affect the entanglement? Does the entanglement degrade due to this velocity mismatch, or does it remain independent of velocity? Well, offhand, I really can't answer this question of quantum entanglement. The only thing that I can answer here is that if there is entanglement between two propagating particles, such as happens in quantum systems, the entanglement must also follow the basic laws of conservation laws of physics, such as the conservation of momentum and conservation of angular momentum. So those things are there. So does the difference in their propagation velocities affect the entanglement? See, in entangled states, particles can move in two different directions also. Nevertheless, they remain entangled. So I'm not, I'm not very sure exactly how difference in velocities may affect the entanglement. But as I said, I really am not very well versed in this particular subject. But once again, I shall try to give an answer by tomorrow. But I hope that the question to the first one, the answer to the first question has been hinted at properly, or if not provided completely. So, with these were the 4 questions that I received from Professor Rajendra. So, so question number 1, I think I have been able to give some clear direction over there. Question number 2, just my educated guess. Question number 3, one part of it answered, I think, I hope. The second part I could not. Similarly, question number 4, beyond the idea that entanglement must obey um, conservation laws, such as the conservation of linear momentum, conservation of angular momentum, I'm afraid I have not yet been able to give anything very concrete. So, with that, I think I may start today's new session. Professor Rajendra, is that all right?
Yes, we can start with the remaining
Um,
concepts.
remaining part. Yes, yes. So yesterday we finished up to this Huygens idea. I would just advise you all to make a very careful note. See, this wavefront formalism. Make a very careful note of case 2. What is case 2? Case 2 is optic axis parallel to the refracting edge, but on the plane of incidence. So here is the dotted line. This is the optic axis. It will be on the plane of incidence but parallel to the refracting edge. So this case will be important. Do also note this diagram. as it happens, because today we shall discuss plates, quarter wave plate and half wave plate. So there, this idea will be very important. Okay, but before that, let us just move on to a little discussion on some basic ideas, because these ideas will be necessary when we discuss optical activity also. So here it is, superposition of two orthogonal waves. Now, yesterday, I hope you will remember my mentioning that I said that any linearly polarized state, a linear state of polarization, can be decomposed into two mutually, I mean, when I say a linearly polarized state, I say that the electric field vector is oscillating with a certain orientation with respect to the x and the y coordinate axes. Mm. So, if I decompose the electric field vector into their two mutually orthogonal components, one will be Ex x cap and the other will be Ey y cap, but the wave is propagating in the z direction, so the scalar function will be will depend, the phase that is will depend on the z and the t coordinates. Okay, so let us introduce a phase difference here. So here it is, I mean, this is what it is. E has got a certain orientation in space. Here it is, and E is a vector sum of Ex and Ey components. So let us write Ex is equal to E naught x. E naught x is the constant amplitude in the x direction, cosine kz minus omega t. Ey is equal to E naught y, cosine kz minus omega t plus a phase difference, epsilon. So here it is. So z-axis is pointing towards the observer. This is to the right is the x-axis, to the towards upwards is y-axis, and pointing to us, those who are looking at the screen, the z-axis you have. So the z-axis is pointing to us. X cross y is z. Okay. So, and the electric field vector is probably somewhere here oscillating up and down. Now, we shall make basic use of some trigonometric identities. Cosine A plus B. Cosine A plus B is cos A plus cos B minus sine A minus sine B. And what is A and what is B here? A is kz minus omega t in the Ey vector, and B is epsilon. So, we will write that thing as cosine kz minus omega t plus epsilon will be written like this: cos kz minus omega t cos epsilon minus sine kz minus omega t into sine epsilon, Ey by E naught y. And then let us look at the other field vector, that is cosine kz minus omega t is Ex by E naught x. So basically we have a situation over here where we can eliminate the this package phase argument, the argument of the phase cosine function kz minus omega t could be eliminated with these two equations. So cos kz minus omega t is Ex by E naught x, and here you have got sine kz minus omega t. That will be by using the usual trigonometric identity, sine squared theta plus cos squared theta is equal to 1. We write sine kz minus omega t is this, and that is also this square root of 1 minus Ex by E naught x whole squared. So this and this we shall substitute in the equation at the bottom of page 23, and here we are. This is the equation that we get. The next task is for us to take this part to the left hand side and square the whole equation, and this is the full squared equation that we get. After that, we defactorize the equation, and this is like, a minus b whole squared. So that's the formula that you have: a squared plus b squared minus 2ab, like that. And on the right hand side, you've got sine squared epsilon minus sine squared epsilon by this. And then this thing, the sine squared epsilon part, we can take to the left hand side, and there you have got a cos squared epsilon. Both of them have the same prefactor, Ex by E naught x whole squared. So it is basically Ex by E naught x whole squared plus, I'm sorry, into cos squared epsilon plus sine squared epsilon, which will be 1. So here we have this situation: Ex by E naught x whole squared plus Ey by E naught y whole squared minus 2 this ex by e naught x into ey by e naught y cos epsilon is equal to sine squared epsilon. By the way, those who are listening to these talks may please also note that I have sent these notes to Professor Rajendra, who I believe will share these notes with you in due course. Okay.
So it's
So,
already shared on the Canvas
uh-huh.
link. I have also shared the
Oh,
reference material.
oh, okay, okay, fine. That will be helpful for everyone then. Okay, so what we shall do now is to look at the orientation of the field with respect to changing values of the phase difference epsilon. Note that our two field functions are these. These are the two field components of the electric field function. So we tune the value of epsilon, and then we shall see what results, what sort of orientation will result. So the first case, case one, we are looking at different values of epsilon now, some simple cases to work with initially. This is actually a simple geometric discussion. There is not much of physics or anything, just mathematical discussion, coordinate geometry and trigonometry. So let's see now. Epsilon is equal to an integral multiple of 2 pi, right? Or even multiple of pi, which is an integral multiple of 2 pi, because when you multiply m by 2, it will always be an even number. So now let us see. So basically, you should read this thing as an integral multiple of 2 pi, although I've written it as 2m into pi. So m can have any integer values. So whenever you have an integral multiple of 2 pi, sine will be 0 and cosine will be 1. So those values we put in this equation, and immediately you can factorize this equation straight away as this: ex by e naught x minus ey by e naught y whole squared is equal. So this is a whole squared now. This is 1 and the right hand side is 0, and as a result you can now solve this equation. This is the equation of a straight line passing through the origin. So you look at this straight line. If you look at this, the right hand side, sorry, the horizontal axis pointing in to the right is the vibration field of the x component of the electric field vector. The vertical is line is the vibration field of the y component of the vibration plane, I'm sorry, of the electric field vector. The plane is passing towards you, and this oblique plane, this is just the projection, three-dimensional projection on a two-dimensional paper. The z-axis, it is as if that we are looking down on this plane along the z-axis. So everything has to be projected along the z-axis towards the viewer. So this is actually a plane wall, this is actually a horizontal floor, and this is some sort of an inclined sheet. But we are looking at all of these three things edge on, and so that is why they are looking like three lines, but actually they are projections of a plane. So ey will be equal to e naught y by e naught x. These are the constant amplitudes. So ey is a variable, ex is a variable. The amplitude value, or sorry, the displacement along the x and the y axes respectively, and this is the slope of the straight line. Now let us look at another case, odd multiple of pi. So it is 2m plus 1. So when you have an odd multiple of pi, sine of epsilon will be equal to 0 and cos of epsilon will be equal to 1. I'm sorry, minus 1. Cos of 0 is 1, cos of pi is minus 1. So similarly, cos of 2 pi is 1, cos of 3 pi is minus 1. So like that, an odd multiple of pi. As soon as you have an odd multiple of pi, let us go back to our equation here. Sine will be 0, of course, on the right hand side. Cosine will be minus 1. So there's a minus here and there's a minus here. The two minuses will make it a plus. And so when you factorize this equation, write it as a perfect square, it is in the form of a plus b whole squared. So this is the equation. This is once again is the same thing, except that now you have got a minus sign. And so the orientation of the field will be this. Uh, Early in the first case, in the case one, it was the equation of a straight line that was passing through the origin and lying in the first and the third quadrants. Now you have the equation of a straight line passing through the origin, lying in the second and the fourth quadrants. So that is what you have. So you have two cases so far discussed. Now we shall go to some interesting case. Uh, epsilon is plus minus pi by 2. So either plus 90 degree or minus 90 degree. So far we have looked at only integral multiples of pi. But now we shall look at half integral values of pi plus 2m pi. One need not really worry about this plus 2m pi because that will always, that's in a cycle that will keep returning the same value. So this is just an overgeneralization really. There was no, I mean, there's no serious involvement of this thing. So now let us see what we have when you have epsilon equal to plus minus 2 pi. Plus 2 pi is actually 90 degrees and minus 2 pi is 270 degrees, plus 270 degrees, right? So that is how it happens. So when you have plus minus in either case, plus minus pi by 2 or plus minus 90 degrees, sine squared epsilon will be equal to 1. Sine squared epsilon is equal to 1. But for sine 90 degree, it is plus 1, and for sine minus 90 degree, it is minus 1. But the squaring will kill the effect of that minus plus difference. Okay, but cosine will be 0. Now let us see what we have here. This equation, cosine is 0, so this part term vanishes and the right hand side becomes 1. Basically now we are looking at the equation of an ellipse. Here it is. So this is the case of elliptical polarization. So earlier in the two previous cases, the tip of the electric field vector would oscillate up and down this line in the first case. In the second case, the tip of the electric field vector would go up and down this line. But here now, the tip of the electric field vector will trace this elliptical path, and its major axis is E naught x and the minor axis will be E naught y. And case 4 is a simple subset of this case 3, where both E naught x and E naught y have the same value. In that case, it will be circular polarization. The tip of the electric field vector will trace out a circle. So I have made a statement over here, which I shall now discuss in detail. When the phase difference has a positive sign, plus pi by 2, the rotation is anti-clockwise, going in the in this direction, positive angle direction. So such a light is known as left circularly polarized light. And when epsilon is minus pi by 2, it is clockwise right circularly polar. So clockwise means it goes down like this. So that will be negative angle going down like this, positive angle going up like this. So that's a simple way to remember, but we shall prove this thing or establish the direction more formally now. But what is the convention of clockwise or anti-clockwise? The light is coming towards you, the viewer. So we are looking at the tip of the electric field vector going up like this if it's plus pi by 2, or going down like this clockwise if it's minus pi by 2. But the light is along the z-axis and the z-axis is pointing towards the viewer. So we are looking at the light head on, like we would look at a train coming head on. So something like that. And the tip of the electric field vector is tracing out these geometrical figures. If the amplitudes are not equal to each other, you have elliptical polarization, and if they're equal to each other, you have circular polarization. So the sense of direction will be important for us to refer to later when we discuss optical activity. But first, now let us establish why it should be anti-clockwise for plus pi by 2 and why it should be clockwise for minus pi by 2. Okay, so we will discuss this thing. We shall discuss it for the simple case of circular polarization, because the sense of direction will be the same in the case of elliptical polarization also. So let us see now. So here we have two vector fields as we started. E naught x and E naught y are no longer different. They have the same value. So Ex is equal to Zt E naught cos kz minus omega t. Ey is Zt E naught cos kz minus omega t plus epsilon. So we decide to freeze on a plane. And on the plane, we then try to see what is the direction of rotation of this field vector, the tip of the field vector. So we choose the z plane, z equal to, sorry, the xy plane. On the xy plane, the z coordinate has the value 0. If that be so, then this first term in the phase will vanish, and you will just be left with Ex is equal to E naught cos of minus omega t, and that is also equal to E naught cos omega t. And E naught 0 t, z equal to 0, will be E naught cos of minus omega t plus epsilon. And so E naught will be equal to cos of minus omega t minus epsilon. And again, the minus sign is killed because cosine is an even function. Okay. Let us now see. Epsilon is equal to minus pi by 2. If it is minus pi by 2, remember that we shall have a clockwise sweep of the tip of the field vector. Let's see how we can argue for that. Ex is equal to E naught cos omega t. That does not depend on epsilon. So we shall just look at the Ey part. Ey is equal to E naught cos omega t. Epsilon is equal to minus pi by 2. So minus and minus is plus pi by 2. Now here's cosine pi by 2 plus omega t is cosine pi by 2 minus of minus omega t. So cos of 90 degree minus an angle will be sine of that angle, and sine of a negative angle will be minus sine omega t. So that is how you argue for this. So this thing is minus E naught sine omega t. Okay. Now, when t is equal to 0, let us see. At t equal to 0, Ex will be E naught into cos of 0 will be E naught, and Ey will be minus E naught of 0. So when you have t equal to 0, Ex will be equal to E naught and Ey will be equal to 0. So when t is equal to 0, this is where we shall lie. Ey has no value, and E naught, sorry, Ex has the value E naught. Now we slowly increase t. Let us say that we increase t to the value of pi by 2 omega. When you increase e to the value of pi by 2 omega, omega t will be equal to pi by 2, right? And t will be equal to, well, so that's what you have. So now Ex is equal to E naught cos omega t. It is equal to E naught cos pi by 2. Ex will become 0, and Ey will become minus, it was minus E naught sine omega t. So it is sine of 90 degree. So 1. So minus E naught. So basically what happens is that as time is increasing at t equal to 0, you were here at this point. At then once you have started increasing t, you have come down here at this point. Basically, the rotation is happening in a clockwise direction for the initial phase angle value of minus pi by 2. Well, of course, you can immediately imagine that it will be the other way around when I write plus pi by 2, but we shall show that also in detail. So this is the case of right circular polarization, clockwise rotation when the initial angle is minus, initial phase difference is minus pi by 2. Now let us look at the other case. Once again, here we have this thing. Ex is equal to E naught cos omega t. Ey is equal to E naught cos omega t minus epsilon. Epsilon is equal to pi by 2. So Ey will be equal to E naught cos omega t minus pi by 2. And so that will be equal to E naught into cos minus pi by 2 minus omega t, even function. So the minus will go away, and so it will be E naught cos of pi by 2 minus omega t, and cos 90 degree minus an angle will be sine of that angle, E naught sine omega t. Again, the same argument you can offer. At t equal to 0, Ex will be equal to E naught and Ey will be equal to 0. So when you have at t equal to 0, Ex is E naught, Ey, you are here on this line. When t is equal to pi by 2 omega, or omega t is equal to pi by 2, then Ex will be equal to E naught cos 90 degree. Ex will come down to this point, 0 it will become, and Ey will be equal to E naught sine 90 degree, and that will be this. This is the angle. So this is the case of left circular polarization, anti-clockwise. Okay. So we said that we have frozen this thing on a plane, on the plane z equal to 0. Suppose we had moved forward to a value of z equal to z naught, some positive value, then your initial phase angle contribution will have k z naught. And so basically this will just amount to whatever discussion that we have had so far. that this angle and I'm sorry, this axis and this axis, it will all be rotated by a simple angular value. This will become the reference axis for Ex, and this will become the reference axis for Ey. And they will these two axes will make an angle of kz naught with respect to the previous set of axes x and y. So that's how this transformation will happen, but the basic principle will be the same. You will move either this way or this way depending on the sign of the initial phase angle difference. Now whatever we have discussed, we shall apply to some practical use, in this case, particular case of retarders. Let us now try to see. What is a retarder? The very name itself is self-suggestive. It retards. And what do I mean by that? Let us now try to see. A retarder is a basically it causes a difference of velocities. One velocity will be suppressed with respect to another. So basically we are going back to the old idea, the same idea of e rays and o rays traveling with two different speeds. Anyway, so let us see retarders, devices to change the polarization of an incident wave, and this device is usually made of birefringent calcite crystal. Okay, so devices to change the polarization of an incident wave. Let us now see. So we have this case, normal incidence with optic axis parallel to the refracting edge. Just at the start of today's discussion, I mentioned to you to make a special note of the case we discussed yesterday. Huygens' principle, wavefront formalism, optic axis parallel to refracting edge, but on the plane of incidence. This is the optic axis. We lift it and we make coincide it with this. This is the dotted line, the optic axis. We coincide it with this horizontal line, right? So that will give us this scenario. Sorry, this scenario that here you have calcite material. It is a negative crystal, which means that the E rays will propagate faster. And so this is the optic axis. Here the two speeds are the same, and it's along the major axis where the E rays will travel at their fastest with respect to the O rays. The O rays have a circular front, whereas the E rays have an elliptical front. That idea we shall now apply in the case of retarders. So retarders are basically devices to introduce a phase angle difference or create a change of polarization state. Okay. So let us have a retarder plate of a certain thickness d. Right. Now, two rays are passing through this retarder plate, one the O ray and the other the E ray. Now, it is a matter of simple theory in geometrical optics that we don't actually follow light. We say that, in geometrical optics, we say that, like in refraction. In refraction, the ray path is bent at the point of impingement. So we say that although typically between 2 points, light travels along the shortest possible path, but geometrically speaking, traveling from one medium to another, light actually appears to take a longer path. And you can see in water or something, a stick will appear bent. So the light looks like that it is taking a longer track to go from one point to another. Actually, a light is traveling not along the shortest geometrical path. In these cases, light travels along the shortest optical path, right? And the short, what is the definition of an optical path? The definition of an optical path is the geometric distance traveled in that path multiplied by the refractive index of the medium in which that path has been traced. So O rays correspond to the refractive index NO. So the optical path traveled by O rays is NO into D, and the optical path traveled by E rays is NE into D, right? And both the rays have traveled the same geometrical path of D, but they have traveled different optical paths of Ne minus No into D. I have taken the absolute value over here because actually Ne is less than No in the case of calcite material, because it's a negative crystal, and E rays travel with greater speed. Therefore, the refractive index of the E ray will be less than the refractive index of the O ray. So I've just taken the absolute difference between the two rays, and so this is the optical path difference, capital lambda. Now the next thing, and so this is the geometrical layout. This is an initially polarized wave that is coming. This is the refracting edge, and the optic axis of the calcite material is also corresponding to this refracting edge. So to the left is air, to the right of this vertical line is the calcite material, which is birefringent material, and the material thickness is D. So air, calcite, and then to the right of this vertical line is again air. Okay. Now as soon as, so here's the polarized light that is incident at this point. The polarized light has been decomposed into two polarization planes. One polarization state is on the page itself, and the other polarization state is perpendicular to this page, right? So these two polarization states you have, and they are impinging at this point. As soon as thereafter, it's simple geometry. We are actually doing geometrical optics. So here the O rays, this is Huygens's wavefront formalism. O rays will travel with a spherical front, or rather in this on 2D, a circular wavefront. But the E rays will travel faster with an elliptical wavefront. And you can immediately see that in terms of the optical path difference, the difference will arise here, the gap between the two. Let us now see. So here it is. The velocity of E rays is C by the refractive index of E rays, and the velocity of O rays is this. And I hope that yesterday we had this discussion that once, let me just go back to that page once again. Sorry, please just bear with me. When light gets into a nickel prism or a calcite, generally a calcite material, this is what happens. Natural light with both states of polarization enters birefringent material, in this case calcite. The E rays contain the state of polarization that is on the page, and the O rays carry off the state of polarization that is off the page, coming out of the page, perpendicular to this page. So it's the same feature that is happening over here in this diagram that I've just shown you. Let me return to that diagram here. Here. The E rays are carrying off the state of polarization that is on the page on this plane, and the O rays here, black dots, they are carrying the state of polarization that is coming out of the page. So the black dots are representing that. So that's how you should. So here the two rays have been separated, or the two waves have been separated, and now they are propagating with their own speed. Okay. So the optical path, after it has traveled through this thickness D, this thickness D, I'm sorry, this thickness D, the optical path that it would have traveled will be Ne into D, and the optical path of the O ray would be No into D, and that's the optical path difference, D into Ne minus No. Right. Okay. So, I mean, if there had been no difference of the refractive indices, then the optical path difference between the two rays would have been 0. Okay. Now let us come to a very basic idea. What is the corresponding phase difference? Phase difference is path difference. In this case, optical path difference, or rather, I'm sorry, just a minute. I'm sorry, the mic has come. Can you all hear me clearly? I'm sorry.
Yes, we
Hello?
can hear you.
Oh, okay. I'm sorry, the mic just kind of fell off. I'm sorry. Okay. So just remember this one thumb rule: phase difference by 2 pi is equal to path difference by a full wavelength, meaning one full cycle in a wave is in the length dimension is wavelength, and phase angle it is 2 pi. And by the way, in time it is one time period, but we are not making use of time over here. So phase difference by 2 pi is equal to path difference by the wavelength. So what wavelength we have to choose over here? We have to be a little careful. We have chosen the vacuum wavelength. This thing is lambda subscript 0. I've written the 0 like this in the as it happens, because there is a subscript O over here, right? So not to confuse with O, I've written the 0 like this, as in the case of a computer keyboard or in computer notation. So that is what it is. So phase difference by 2 pi is equal to path difference by the wavelength. And so therefore delta phi by 2 pi will be path difference by the wavelength. But here we have to be a little careful. It's not just the path difference, it is the optical path difference by the wavelength. Therefore, that is the required formula. D, what is the necessary thickness of the plate that you need to employ? D will be equal to the required phase difference times the wavelength of the light that we are using over here, monochromatic. Uh, by the way, do note one thing, that in all of these cases, the speed of light is changing, which means that the wavelength is also changing, right? But the frequency is not changing. That is why we need to have a fixed reference wavelength. That's why we are not talking about the wavelength of light in this media, in this medium. We are talking about the wavelength of light as it should be in vacuum, where there will be no optical path difference. So that is the reason why we have especially insist or prescribed this condition. So delta phi is equal to this. Now, what about a full wave plate? For a full wave, the phase difference will be 2 pi or an even multiple of pi. Or integral multiples of 2 pi. Full wave corresponds to 2 pi phase difference. So that is the case of a full wave plate. So once you have this thing in this formula above, delta phi, you write 2 pi. And so you write 2 pi by the wavelength into d into ne minus n naught is equal to 2 pi. The 2 pi will cancel, and so d will be equal to lambda naught uh, vacuum wavelength divided by ne minus no. Of course, when you have a phase difference of 2 pi, effectively, there is no phase shift. The two waves are overlapping each other. So that is how you have. Okay, so if you choose uh, a, a plate thickness given by this quantity, the thickness of the plate is the wavelength divided by the refractive index difference, the absolute value, vacuum wavelength by this thing, you will introduce no phase shift at all. Now we have to look at two other cases. One is the half wave plate. When you say half wave means this case, that here delta phi will be equal to pi, which is an odd multiple of pi, right? So when you have an odd multiple of pi, 2 pi by lambda naught, this is the formula. This formula we are using. Delta phi is equal to 2 pi by the vacuum wavelength into d. So here we shall just write pi on the left hand side, and the pi's will cancel. And sorry, for the case of the half wavelength, pi's will cancel. And so d will be equal to lambda naught by 2, so divided by the difference of the refractive indices. So what effectively this will do is that rotate the plane of polarization of linearly polarized light by an angle 2 theta. What do I mean by 2 theta? So let's just look at this thing geometrically a little. So here, think of this thing. Here the light wave is entering with a certain state of polarization, a certain orientation. The vertical projection of that orientation is on this plane of the paper, and the horizontal projection is away from the plane. So if you look at it head on, so the light will be approaching you. You are the observer standing over here somewhere and looking at the light approaching you head on. Let us say that this is the way the light is approaching you. This is the line of orientation along which the light is approaching you. Z axis is pointing towards you. This is the plane of orientation. and the vertical axis is the projection of the polarization on the plane of the paper, and the horizontal axis is the projection away from the plane of the paper. So what will happen is that if you make that light pass through a half wave plate, immediately on emerging at the end of the plate, if the light wave emerges from this side of the plate, its orientation will change to this side. How so? We have just discussed that basically the purpose of the half wave plate is to introduce a phase angle difference of pi, right? Just a while ago we discussed this thing. Suppose you have a light wave that is coming like this, with a certain this orientation. If you suddenly introduce a phase angle of pi to that, immediately it will flip to the other side. The slope, the value of the slope will remain the same, except that it will pick up a minus sign. So that is what has happened here. So the purpose of a retarder plate with a half wave retarder plate is to introduce a phase angle of pi and create a path, an orientation difference like that. Now you can, by the same argument, just some time ago we discussed that if you have a phase angle difference of pi by 2, then there will be a rotational behavior. The tip of the electric field vector will start sweeping out either an elliptical path or elliptical locus or a circular locus. Circular locus if the x amplitude and the y amplitude have the same value. So here it is, quarter wave plate, delta phi is equal to pi by 2 phase angle difference, and so this is what you will have. On introducing a phase angle difference of pi by 2, you will get elliptical polarization or circular polarization if this thing is the two components are the same. How am I getting this thing? We just argued. I'll just quickly flip back to those pages and remind you of this thing. So here, this was the discussion, that you introduce a phase angle difference of pi by 2, and either way, plus or minus, doesn't matter. The tip of the electric field vector will start rotating over an elliptical locus if these two values are not the same, and if they're same, then the tip will have a circular sweep. Okay, so that is what we have now. We have discussed retarders. Now, with the idea of retarders, we shall see how we can analyze polarized light. So this is a new
Can
topic.
we take 5 minutes break here if
Yes,
it's a
yes, yes, yes.
logical?
Yes. This is a logical new topic, right? So today we
Okay.
shall discuss 4 topics. We have finished 2. This is the start of the third topic. So we can
Okay.
have a 5-minute break.
All right.
Okay,
All right.
no
Thanks.
problem. Thank you. Thank you.
You are actually sharing your complete screen, so probably